Hello there. Welcome to another presentation of our e-tutorial series. My name is Charles Welsfani Msipa. Our presentation now is on how to obtain a particular solution to the differential equation which originates from Newton's law of cooling.
Okay guys, let's take advantage of what we have looked at and try to do something I would call some mathematics of a cup of tea or a cup of coffee, your choice. Alright, the situation here is as follows. We're given here a cup of tea or a cup of coffee or hot chocolate which is at 95 degrees Celsius. And the room temperature, when we start observing this temperature, this experiment, is at 25 degrees Celsius, which is normal temperature in most parts of our country. And we're told also that after 2 minutes, the temperature of this tea is at 69 degrees Celsius. But remember that the Newton's law of cooling made us arrive at this model which gives us a function of time which delivers temperature of the object which is cooling down, and that model is y of t equal to A0 by e to the power kt plus the ambient temperature, that is the room temperature or the surrounding temperature. So now, if we were to find this function which describes this particular situation, given these initial conditions, the task consists in determining the value of A0 and also determining the value of K. So those are the parameters you need to determine, since you were given already that the ambient temperature is 25 degrees. And in this case, our 95 degrees, which is the temperature of the tea, is actually our initial temperature that will give us the initial value of the function in this case, which is y at 0. We consider temperature time t equal to 0 when we start observing this experiment. So y of 0 will be equals to A0 e to the power k times 0 plus our ambient temperature, which is 25 degrees, and that will be 95. That will be equals to 95. Now, simplifying that, I hope you can see that you notice that e to the power 0 is 1 times A0 is A0. Then, therefore, from this equation, we get that therefore A0 is equals to 95 minus 25, which is equal to 70 degrees Celsius. Now it's subtracting on both sides of this equation 25, we get 70. So now we can now rewrite the model as 70 e to the power k t plus 25. So now we've achieved partly what we were supposed to do to get the value of a, then the function now we can express it this way. So the next thing to do is to use this initial condition, which says after 2 minutes, the temperature stands at 69 degrees. So what we have here, we need to now evaluate this function at 2, and we're told that it is going to be equal to 69 degrees Celsius, which implies that the value of this expression, substituting T by 2 is going to give us 69. So we write here 70 e to the power 2k plus 25, that is equals to 69. Then what we're going to do now, we need to now subtract on both sides 25, which is going to give us this equation is equivalent to 70e 2k equals to, in this case, to subtract 25 on both sides of this equation, with 69 minus 25 would be 4 and 4. Now it's going to be equal to 44. Then we continue as dividing both sides here by 70. We're going to get e to the power 2k equals to 44 divided by 70. So now remember, at this stage now, our target is to get the value of k. So now, having a k in the exponent here, we need to appeal to the inverse function, inverse to the exponential function, which is ln. Then applying ln on both sides, we are going to have ln a2 k is equal to ln 44 over 70. And then what we have here, we've got, we're going to have this equivalent to saying that 2k is equals to ln 44 over 70. And then we can say, therefore, k is equals to ln 44 over 70 divided by 2. I hope you notice that already, because this T is cooling down, and from our previous discussion, we should be expecting our K to be less than 1, so to be less than 0. And this is exactly the case. Remember, the graph of a ln function or any logarithm function is of this shape. It has got a 0 at 1, and it grows rapidly before 1, then gently after 1 like that. So before 1, the values of ln are less than 0, and clearly 44 over 70 is less than 1. So we can simplify this to some decimal number, which is negative. And if I'm not mistaken, this simplifies to, you can check my numerical values later, but I got a number equals to 0 minus 0, 0, 1 to, let's say, correct to 2 decimal places, but I can double check that. But most important, you can see there is less than 1. So now having our A0 obtained, our K obtained, now we can write the function which describes this particular situation of a cup of tea or coffee as y of t equals to our A, which is 70, e to the power minus 0, 0, I think it's 0,001, sorry, 0,001, T plus the ambient temperature, which is 25 degrees. So now what we've arrived at now here is a model which is y of t equals to 70 to the power minus 0.001t plus 25. So this is a particular function which describes exactly how the temperature of the cup of tea is changing there. So now comparing what we have here and this general model we've got there, we'll say this is a general solution for the differential equation which arises from the Newton's law of cooling. And now this, what we've got here, is a function which satisfies the initial conditions which were given there. Then this is called a particular solution to the differential equation. So this is a particular solution. Please note that we call this a particular solution only after having determined the parameter like A. Obviously, in a particular problem, the ambient temperature will be given and also determine the parameter K. And this first solution you had there would call it a general solution. So otherwise, I hope you've noticed, you've taken note of the process which is involved here. You have a particular situation, we know a general model, now you want the model which describes this particular solution, so you have got to take account of your initial conditions which are given, use them to find particular values, then you arrive at a solution. I hope with this example and what we've discussed before, you are able to set yourself on fire and you do this kind of practice until you are very fluent in this kind of solving this kind of problems. Others, for now, I would like to say thank you for listening.